Hello and welcome to a new chapter in machine dynamics, and this chapter is entitled Balancing of Rigid and Elastic Rotors, and most of the chapter will deal with rigid rotors only. So an imbalance has been already studied in the last chapter, and I would say in depth studied in that last chapter for elastic rotors. The imbalance that existed there is shown here in the first figure, namely that the center of gravity is not on the theoretical axis of rotation, that axis that connects the two centers of the bearings. There is a deviation in eccentricity, and that eccentricity leads to an imbalance due to the fact that due to the rotation, the mass can be seen as being concentrated in the center of gravity, and then there are accelerations, and these accelerations cause forces, bearing forces, and these bearing forces grow for high-speed rotors. Now there is a second kind of imbalance. I termed this kind of imbalance a static imbalance. Well, the terminology could be doubtful, but I think it makes a little bit sense. The other one is a dynamic imbalance, namely it is not related to the center of gravity. That is, as you can see here, aligned with the axis of rotation. However, the axis of the principal axis of inertia, the principal axis for the mass moment of inertia, as you can see here, the axis of symmetry for that rotor, is not aligned with that axis of rotation, with that axis that connects this center point of the two bearings. These two kinds of imbalance are present in rigid and also, of course, in elastic rotors, and I will study with you the effect of these two imbalances, and finally we want to remove them. So I will also study with you the balancing of rigid and elastic rotors, and we will analyze a balancing machine in more detail. This will be done in the next video. In this video, I will study with you the effect of an imbalance, and finally possible countermeasures. And the technique of balancing will be studied in the second video. So there are two videos for this chapter. So let's move to the equations of motion in order to understand better what happens here at the bearings when such a rotor with an imbalance, albeit a static or a dynamic imbalance, starts to rotate. So our equations of motion. First of all, we have to ask the question whether we are allowed to use the rigid body assumption here. And the answer is yes. It is allowed if the rotational velocity is half than the critical rotational velocity, so half of the critical speed. If you remember the magnification factor that we studied many times for the Jeffcott rotor, then you remember that once we are in the subcritical regime, or if omega is close to zero, we have conditions that are rather static conditions. So where the Jeffcott rotor behaves as in the static case for a rigid body. And this is exactly here the point. So if we are in the subcritical range, then we can, so in the very strong subcritical range, half than the critical rotational velocity, then we can make use of that rigid body assumption, and we can treat our rotor as a rigid block of mass. Now let's have a closer look on that rigid block of mass. So here you can see it. So this is the rotor. The coordinate system has now slightly been changed here. You can see that there is the x-axis and the y-axis pointing to the vertical and the lateral direction, and now the z-axis is the axis of rotation. So in contrast to our last video, I should, I think, point in that direction if you follow the zeta here. Psi, eta, and zeta are body fixed coordinates. They are the coordinates that we will use for the center for the principal axis for for the mass moment of inertia. And well, if you look at these bearing forces here, then you find the x and the y bearing forces. And the question is, are they co-rotational vectors, these forces, or are they with respect to these axes, x and y? If you have a close look on these forces, then you can see that they are parallel to the psi and the eta coordinate, so they are co-rotational. And now let me point to another specialty of these co-rotational body fixed angles. You can see the eccentricity here of the center of gravity. You can see that the coordinate system, the eta axis, has been chosen in such a way that S is on the eta axis. That means that if you think of during rotation, of a circular motion of the center of gravity, and you think that all the mass is concentrated on that center of gravity. Now, if you imagine that this would be the case, you would have a mass point that carries out a circular motion. That circular motion could be accelerated, of course, and you will find then a radial acceleration, and the radial acceleration is aligned to the eta direction. The psi direction now, if you look at that rotation, so the rotation is around the zeta axis. So you take your right hand here, and then you see the rotation with respect to zeta, and you can see that the psi axis is, well, of course, tangential to that circular motion, but opposite to the classical circumferential direction. So this will be, of course, of importance if we study later on the accelerations in eta and psi directions, because we will use the body fixed coordinates here. They are the most appropriate coordinates in order to formulate the problem. These body fixed coordinates are not the coordinates of the principal axis, because we are dealing with an imbalance, also with a dynamic imbalance. So we have to take into account the fully fledged, I would say, so the full mass moment of inertia tensor, not only a diagonal tensor, but also we have to take into account the off-diagonal elements. So after this, these few words, I would like to start with first the two general laws we are using here in order to derive the equations of motion, namely the balance of linear momentum and the balance of angular momentum. The balance of angular momentum is carried out around point 0, and you can find point 0 here. And you can see it's a space-fixed point because it's on the axis of rotation, but it's also a body-fixed point because it belongs, of course, to that rigid body. So please keep in mind we are dealing here with a rigid body. We are not dealing with any bending or flexural motion here of that body. It's a rigid body. So these are the two equations that describe the motion of that rigid body. And now let's start, well, with the second equation first, so with the angular momentum balance. And we want to formulate it in co-rotational coordinates. So what do we know about the angular momentum? We know that it is equal, so there's a linear relationship between the rotational velocity, omega, and that linear relationship is, well, represented by the mass moment of inertia tensor. So it's not a simple scalar coefficient, unfortunately, that makes rotational motion so difficult to describe, but it's a second order tensor here. So in order to be able to use or make use of that result here for the angular momentum, in the angular momentum balance, we have to take the time derivative. The time derivative is now carried out in the co-rotational coordinates. So as the co-rotational coordinates, or the axis, the psi and zeta and eta axis, or psi and eta axis only, are time dependent. We have to be very careful when we take the derivatives here. First of all, g, our mass moment of inertia tensor, is like, for example, the mass time independent. The only possibility to have a time dependent is if something changes during motion. So your rotor change shape, but it's a rigid rotor, or you lose some part of it, which I don't hope is the case. So J is a constant with respect to time. From omega, we take the derivative, that's indicated here by the prime, of the coefficients of that omega vector represented in the co-rotational coordinates. And finally, from that vector representation, J omega, of the angular momentum balance in co-rotational coordinates, we have to take into account the time dependence of the co-rotational coordinates. And this is done according to the classical Euler-Poisson differentiation formula by the rotational vector omega, because our co-rotational coordinate system, otherwise it wouldn't be co-rotational, rotates with rotational speed omega. Yeah. So this is the equation, and what can be said about the members in these equations? Well, for J, I already said it's a fully fledged mass moment of inertia tensor, so taking the off-diagonal elements into account, but of course knowing that's a symmetric second-order tensor. You can see it from the off-diagonal elements here. And for omega, we just have one component for the moment at least, namely omega in zeta direction, so the rotation of the rotor. You can see that in the diagram I added some other things here. A driving torque, MA, from the German word Antrieb, Antriebsmoment. And finally a resistance torque, K omega, which will come into play, of course, on the right-hand side of that equation. So let's have a closer look on the whole equation. So what do we have here? Well, this was J, this was omega. We have to take the derivative, time derivative of the coefficients of omega, so just write omega dot instead of J, instead of omega, of course, and then multiply G by that omega dot, and then you will find out that you just cut out the last column of the J matrix here of that tensor representation by a matrix here in these co-rotational coordinates. So this will yield the first term on the left-hand side, the first term in that sum here. The second term is obtained by multiplying or taking the cross product of omega with that result, G times omega. So again, you cut out the last column of that G matrix, you multiply each entry by omega, and then you take the product of omega, vector product of omega and J omega. And what you find is then you will find only entries in the first and the second row, because omega has just one component in the last row, and that component in the first row is just J eta zeta omega squared minus J eta zeta omega squared, and in the second row we will have J psi omega squared. When it comes to the right-hand side, in zeta direction, you will find the driving torque minus the resistance torque. And for the other two directions, so psi and eta, you will have to take into account, of course, the bearing forces that are multiplied here by the corresponding levers. So if you take the momentum balance, angular momentum balance around the psi axis, so our first axis here, then you will find an influence of y2, which then rotates in a positive sense. So you take the lever L2 and you get the positive sign, and opposed to this you have the motion of, or would have the torque that is due to y1 with the lever L1 here. Same for the second equation. So now you take into account the balance of angular momentum around the eta axis, and you have to take into account therefore the lateral bearing forces x sub 1 and x sub 2, and now x1 L1 is in the positive sense of rotation, and x2 L2 is in the negative sense of rotation. I think that's no problem for you. So this is the angular momentum balance, or the second part of these two balance laws we have to use in order to obtain the equations of motion. Well, do you see already any unknown here in these equations of motion? Of course, you see that this equation of motion governs omega. Yeah? But omega would be, of course, one unknown described by the last equation, which can be used, for example, to derive stationary states. Once we have a stationary state, well, we cannot use that last equation, we will see that there are four unknowns here. X sub 1, X sub 2, Y sub 1 and Y sub 2, because you do not know the reaction force at the bearings. So four unknowns, but only three equations, and total 5 unknowns with omega. So we need, of course, also the balance of linear momentum here. The balance of linear momentum is written down here. So it is the time derivative of the linear momentum that is represented according to the theorem of the center of gravity by the product of the mass with the acceleration of the center of gravity. And for that acceleration of the center of gravity, let me remind to you that the center of gravity is on a circular motion here around the axis of rotation. That eta is the radial direction, so therefore minus e omega squared for, well, the centrifugal force, or this kind, it's pointing opposite to the radial direction, the acceleration m minus e omega squared. And let me remind that the xi-axis is chosen, perhaps a little bit special here, opposite to the tangential direction, so in tangential but opposite to the tangential direction, and therefore you have a negative sign here, minus e omega dot for the tangential acceleration. That has to be taken into account. In this tangential direction we have, of course, the bearing forces x sub 1 plus x sub 2, and in radial direction we have the bearing forces y sub 1 and y sub 2. And you see that the last equation is not useful. It's nice, a nice balance between 0 and 0, but it's not useful for our investigation here. It would be useful if you have an axial bearings, of course. If you have an axial bearing and if you have some kind of axial motion, or the possibility at least that your rotor carries out some kind of axial motion, then you need an axial bearing, and then you have axial bearing forces, but these are not considered here. So we are considering the radial and the tangential bearing forces, but not any axial bearing. In the whole chapter we will not deal, and also in the whole course we will not deal with axial bearings. It's a nice subject, of course, and there are nice solutions for that, but off the scope of this lecture series. So let me move to the equation of motion that determines, or that governs, the rotation of the rotor first, and after that let's study the stationary state and the outcome for our four bearing forces here. So the differential equation for the rotational velocity is just given by g psi at zeta by omega dot, and this should be balanced, one could say the system torque here by ma, the driving torque by ma minus q omega. So this would be the system torque and this would be the driving torque, and there should be balance between system torque and driving torque, as we have seen before for the Jeffcott rotor. I would like to make two examples in order to investigate whether there is always a stationary solution or not. The first example is something that is not realistic, I have to admit. It's the case that the driving torque is constant, because you cannot have a constant driving torque for all values of omega. If omega becomes too large, then the power supply to your system will come to its limits, of course, and then it's not possible to maintain a constant driving torque, because the power supply to your system is limited. So for that problem, ma being a constant, we have a initial value problem, so a partial ordinary differential equation with some initial condition. The ordinary differential equation has been now written in a little bit different way. I took the term k omega minus k omega and put it to the left-hand side. So we have the variable omega, the function omega that we would like to compute. We would like to compute the time dependence of omega here, especially stationary solutions on the left-hand side, and on the right-hand side we have our constant here. The solution is composed, of course, by the solution to the homogeneous equation and then one particular solution, the solution to that homogeneous differential equation as being a linear ordinary differential equation, first order linear ordinary differential equation, is, I think, well known to you. You can obtain it by that exponential setting, and it is just a c integration constant exponential minus k divided by j zeta times t. If you take that exponential, you take the first derivative, then you see that these two terms on the left-hand side balance, and the result is 0, which is good because we are dealing here with the solution of the homogeneous ordinary differential equation where m(a) naught is changed to 0 then. Finally, we need one particular solution for omega, for our rotational speed, and as MAO is a constant here, it's assumed to be a constant, then we can just assume that omega is also omega. Particular solution is also a constant, and then you can see that you just have to divide by k in order to balance the MA naught, and the first derivative of omega will vanish because we assumed it's a constant. So this is the solution. That solution contains one parameter, integration constant c. So we have to make use of that initial condition in order to determine c. And if this is done, so what you then will obtain is where you take t equal to 0 here, and then you can determine c as being the difference of omega naught minus ma naught divided by k. So we have ma naught divided by k, the negative sign, and that exponential here coming from c. We have ma naught divided by k with that 1 here coming from the particular solution, and on the other hand, from that initial condition, we also have a term omega naught exponential minus k j zeta t. That's nice because you see all these exponential terms here that tend to 0 due to that negative sign, and k and g zeta being positive constants here, exponentially fast if t increases, so very, very quickly. So finally we find the stationary rotational velocity to be equal to ma naught divided by k, like this. Everything seems to be nice, and it seems to be the case that we always obtain such a stationary rotational velocity. Well, except for one particular case, which is of course also an academic case, I have to admit. The case that there is no resistance here. When k is equal to 0, then you see that this result wouldn't make much sense. We have to start earlier. We have to go back to our ordinary differential equation because we drop out, we lose the term that is proportional to omega here in the ordinary differential equation. We just have the first order derivative, and then the solution changes. The solution of the homogeneous equation is now just ma naught divided by j zeta times t, and if you take t equal to 0, then you just have omega naught. In this case, however, you can see there is no stationary rotational velocity because you have a linear increase of omega, of the rotational velocity. As I said, your power supply is limited, and this is not possible. This is not a result that is of importance in practice. So just to show you that there could be cases where a stationary operation is not possible, I would like to show you some diagrams on this, just to give you visible information on the solution. So in the first diagram, you see omega over t. the development of omega over time. First, we take the case into account that we have some kind of resistance. Then we approach the stationary operation here, the stationary operation exponentially fast. And this would be that you start at some value, initial value of omega naught, and then the rotational speed tends to increase until it reaches its stationary limit. However, you can find here the slope, and you will, if there is no resistance, the omega value will increase along that slope and will tend to infinity. As I said, theoretical result. If we look at some other diagram, just to show you how you can analyze that problem again of finding the points of stationary operation, in terms of this characteristic curve, we analyze the system characteristic curve, which is now, which takes now the resistance into account, k omega, and the driving characteristic curve, which is just the external excitation, I would say. And if we have a point where these two lines cross, then this would be the point of stationary operation. Now you can see if the system characteristic curve is computed for k equal to 0, you get a parallel line to the omega axis. So the two lines are, because there are two constants here with respect, or independent terms independent with respect to omega, the driving characteristic curve and the system characteristic curve are both independent of omega, but they are parallel to each other. They do not cross, or as the mathematician says, what is very, very nice, they cross at infinity, these lines, these parallels. That doesn't help you, but it's not a realistic case. So this is just to visualize these results. Let's now move to a more realistic case, to the case that we have a linear falling drive torque characteristic, like this. 1 minus lowercase omega divided by some uppercase omega, which is used here in order to normalize that term here, in order to be able to add or remove it from 1. Yeah? If you insert this term into the equation of motion and you put everything that is related to omega, lowercase omega, of course, on the left-hand side, then your ordinary differential equation changes. The first order term is still the same, but the term that is proportional to omega now has a different coefficient, k plus ma naught divided by capital omega. But for you, for the mathematician, I would say there's no difference. It's still a linear ordinary differential equation of first order, and the coefficients are still constant, are still independent of time. So you just denote that constant here by some k tilde or whatsoever, and you can use the solution that you have studied before. So therefore, I would say for some didactical reasons, it makes sense to start with example 1, although I know that it is not of practical importance. So this case will be of practical importance and can be studied by the same method. So you look at your solution and you write down the solution that you obtained before, where you replace your k now by k plus ma naught divided by omega. So this is the case here for the leading factor, and this is the case for the factor in the numerator of the exponential here. You see, there are 3 places where you have to replace k by k plus ma naught divided by capital omega. And then you can see that even if k is equal to 0, stationary operation is always possible, because you have that falling line for the driving torque characteristic. So you take into account that your power supply is limited. So, and then let's look how the solution looks like. It's the same curve. You will have a stationary point here at ma naught divided by, let's call it k tilde, so k plus ma naught divided by omega. This is the value which is reached as in stationary operation for omega. And you start at omega naught, and then you have that increase until saturation, until you reach that stationary point here. Well, and what can be said if k tends to be very, very small? which would be nice, of course, to have very few resistance here, if the resistance is at least not related to some useful thing, but to some losses due to friction or aerodynamic damping or whatsoever. So if K is very, very small, then you obtain that the stationary operation is capital omega. Is capital omega, so that constant that has been used here to make the term non-dimensional. Okay. Finally, we can also look at the characteristic curve, where now the system characteristic curve has to take into account that coefficient here. So we balance this coefficient with respect to omega and MA naught. So we have two lines, the falling line of the driving characteristic curve and the increasing line of the system characteristic curve, which increases, so the torque increases with linearly with omega. And these two lines, they have to cross. So there must be, and there is always, a stationary operation possible. Okay, let's move a step further to even some more practical importance. So how could this drive torque can be realized? Just one example, a rotor with a direct current drive. So how is it, well, represented? It's the classical representation that you know from your study of electricity or electric engineering. We have here some supply of voltage. We have a coil here, induction coil, we have a resistance, and finally we have our engine, our DC engine, and here we take K omega, so some proportionality with respect to the rotational speed as the loss in voltage. Our equations are now twofold. The first equation is the classical equation that comes from rotor dynamics on the left-hand side. On the right-hand side, I put in now a product of the amperage times some coefficient, some linear coefficient. On the other hand, I have to take into account now Kirchhoff's law in order to analyze that circuit. Well, in terms of, let me allow to speak as a guy from engineering mechanics, I would call this a balance law for the voltage. Yeah? So you have one balance law for the torque and one balance law for the voltage here. Yeah? And on the right hand side you will find the voltage that you supply to the system minus the voltage loss here, which is proportional to omega. On the left hand side you find the voltage coming from the induction coil and the voltage due to the resistance here. If we look at stationary operation again, then we will drop the first terms on these two sides. So you have a balance of K omega and KWI, and you have in the second equation a balance between RMI and UM minus K omega multiplied by omega. So we have two unknowns here, the amperage and the rotational speed omega, and we can solve the second equation for I and insert the result in the first equation. So what do we obtain then? We obtain that K omega is equal to K sub W UM minus KW omega divided by RM. This result can now be inserted as we have a balance between K omega and KWI in the first equation. And if you look, well, the solution is already shown here on the slide. If you look at the representation of that function here, and you look where you have your omega, then you find it's represented the same way as what we studied before on the slide. It's a linear falling characteristic for the drive torque. The first term is the constant, UM divided by RM. the second term would represent omega divided by capital omega. So your capital omega would be K sub W divided by R sub M if you take K W for MA naught. Yeah? But of course you have, no, that's not correct, because we have to make the first term non-dimensional and amount it to 1. So we have to write UM divided by RM in front of the KW. And then you can do, of course, the computations and obtain capital omegas. Yeah. So you have to make a comparison of coefficients. There must be a 1 here. So MA naught is K sub W times UM divided by RM. And from that you can obtain capital omega. But what I wanted to show to you is only the fact that we have a linear falling drive torque characteristic here. So our second example was quite realistic, I would say, yeah? And represents a classical case where you have a coupling between a direct current drive and your rotor system. So this being said, I would like to move to the other 4 equations that we have to study. Namely, we assume now that we are in a stationary state, and then our remaining 4 equations of motion. Keep in mind that we have already studied the third equation for the angular momentum balance, which leads to the stationary operation, and we have lost the third equation of the linear momentum balance because it's just a trivial equation. 0 is equal to 0 because we have no axial bearing here. So if you then set all the terms in omega dot to 0 because you're in a stationary case, you obtain these 4 equations. And you can see that these 4 equations are linear equations in the forces. So this is the big advantage to use a body fixed coordinate system. You have time-independent forces in the body fixed coordinates, and you have a linear system, and this linear system is now easy to solve. The solution, I don't want to bother you with the details here. It's technical to solve for equations to 4 unknown, for linear equations to 4 unknown, but the solution is of interest. Why? Because first of all, what you can see is you have a dependence on omega squared. The bearing forces are depending on omega squared, which is the classical case for a mass force excitation, as you have seen, for example, in the first real chapter on vibration isolation, and of course also for the Jeffcoat rotor. So that there's no surprise that if you increase the rotational speed, the bearing forces will increase with the square of the rotational speed. And this is the reason why we have to balance our rotor, because they can quickly become large, especially for high-speed rotors. And then what is of interest to see what is the effect of what I called at the very beginning a static imbalance, and what is the influence of a dynamic imbalance. So the dynamic imbalance is represented by the off-diagonal elements of the mass moment of inertia tensor. You can see that certain, namely the same off-diagonal elements, are represented in x sub 1 and x sub 2, and 2 others are represented in y sub 1 and y sub 2. So in the radial forces and in the tangential forces. So if you measure these forces, you can get an idea of the influence or of the size of these off-diagonal terms with respect to the other off-diagonal term here. And there is also present the effect of the static imbalance, and the effect of the static imbalance due to the choice of the axis here is only visible in the radial axis, because if we have chosen our axis here such that the center of gravity lies on the eta axis, and y1 and y2 are the forces in eta direction. Keep that in mind. Yeah? Okay, so that can be seen. Let me summarize the result, and then we will discuss what we could do against it and how we can reduce these bearing forces. So the result is the bearing forces are proportional to omega squared, which is dangerous. The bearing forces are co-rotational forces. You've seen they are constant in the co-rotational coordinates, time independent. There is mass force excitation, as studied many times now in this lecture. There is a static balancing necessary, so reduce E to 0. At least this is necessary in order to keep the radial forces small. This can be done by simple swinging, so balancing the center of gravity in order to determine E, and then to do some countermeasures. And finally, there's also some dynamic balancing necessary, which can be done in balancing machines to reduce the off-diagonal elements of the mass moment of inertia tensor to 0. So assure that the principal axis of your rotor are moved back to the, or at least the main principal axis, to the axis of rotation. Okay, now how can this be achieved? Here's one proposal. A balancing can be achieved, at least for stationary operation, by 2 point masses in 2 planes that are perpendicular to the axis of rotation. Well, if you look at that figure, then you can find these 2 masses, these 2 balancing planes, well, to the left and to the right, because there's some space of the rotor, to the left and to the right. So it must be 2 planes, not the same plane. You can find a mass point, an additional mass point in each of these planes, and you have then the force here, the centrifugal force, as we are dealing with the stationary operation only. And you have 4 equations. The 4 equations we had before, they have to be now modified due to the fact that we introduced 2 new forces here. 4 equations, we have 4 bearing forces, and we would like to have all these 4 bearing forces equal to 0. And this is achieved, well, by 2 forces that are generated that should counteract, so reduce the bearing forces to 0. Now you could ask, well, but there are 4 bearing forces and just 2 radial forces, but there are a lot more parameters in that system. The choice of the plane would be one additional parameter, but also the choice of the mass here, the distance in which, so the radius of the circle on which this mass rotates with the rotor, and finally also the inclination angles phi sub 1 and phi sub 2. So believe me, there are more than enough parameters, and you won't use all of these parameters, for example, for your car if you balance the axle of your car. So these are the centrifugal forces. Let's introduce these centrifugal forces in the balance of force or linear momentum and in the balance of angular momentum, or in the balance of angular momentum, of the torques. So we project F1 and F2 to the psi axis. There are no other influences. Well, there would be some other influences. You would like, maybe you ask, where are the bearing forces? But keep in mind that our objective is to reduce the bearing forces for 0. So I assume 0 bearing forces here in the balance, in the force and or in the balance of linear and angular momentum. So therefore, the terms related to the bearing forces are not included here. That is, if this balance holds for these 2 additional forces, F sub 1 and F sub 2, then the bearing forces have to be 0. Otherwise, there wouldn't be a balance for the whole equations. No? So write down the equations that you have seen before, equations of motion, set all the bearing forces to 0 and add the terms that play now would say, or counteract these balance forces, these bearing forces, include the forces from the balancing masses here. Then we have to project them, as I said, to the xi-axis by the cosine functions. That leads to the first equation. We have to project them to the eta axis. That leads to the second equation, and we have to add here me omega squared, the tangential, opposite tangential force here, and inertia force. And we have then to take into account the rotation of these forces, I would say, around the xi-axis. So this was our xi-axis here. F1, A1 would rotate in this sense. So you will find a sine phi 1. And you will find F2 sine phi 2, A2 for F2, and this has to be multiplied by A2 and here by minus A sub 1. And well, the same for the second equation. You consider again the rotation around the eta axis. You take the projection of the forces as before on the xi-axis then, and you multiply with the appropriate lever, and you obtain the fourth equation here of motion. So you have 4 equations in order to determine your parameters. So in order to determine your balancing masses, and you can see that inside these balancing masses you have parameters, namely you can vary the mass, but you can also vary the radius here. You can see that well, the effect is the same if you vary the mass or if you vary the radius. So this depends on your choice. So for example, if you have to fix that balancing mass somewhere on your wheel, then there will be a limited choice for the values of R, and this also then will limits the choice for M, for the mass itself. Yeah? So you have more parameters. You have M, R, phi, and A1A. So you have at 8 parameters, but just 4 equations. And what you can see is that these equations are now nonlinear in the parameters. The nonlinearity is already manifest here for M1 and R1. One could say it's a trivial nonlinearity. It leads not to very complicated solutions. It's included here in the cosine and in the sine functions, but also this is not a problem. Think of trigonometric Pythagoras to solve that problem. And then we have here another multiplication by A sub 1 and A sub 2. Yeah? So usually what is done is you consider the linear equations in M1 R1 sine phi 1, M1 R1 cosine phi 1, M2 R2 sine phi 2, and M2 R2 cosine phi 2. You fix the balancing planes. They are fixed for the axle of your car, for example. You have not much choice where to place these masses, or where to place the balancing planes here. So suppose A sub 1 and A sub 2 are fixed. Then you have these 4 linear equations and these 4 quantities, and what you want to determine is M sub 1, R sub 1, a product, yeah? And on the other hand, phi 1, and the same with 2, M sub 2, R2, and phi 2. These would be the 4 parameters you want to determine. All of the other quantities are fixed. Yeah? The result will be independent of omega. This can be shown. So that is that balancing holds for any value of omega. That's good. Otherwise, well, you have to change. If you drive faster, you would have to change the balancing mass, and that's not feasible. Yeah? So, and as I said, in practice, A1, A2, and also R1 and R2 are given, and you determine M1, M2, phi sub 1 and phi sub 2. So I could say perfect. And that's it. See you in the next video. But no, the most of the part of the work is not done. Why? Because do you know the tiny e here of the axle of your car? Do you know that that where the center of gravity is exactly located with respect to the axis of rotation of that axle? Do you know the deviations of the mass moment of inertia tensor, so the off-diagonal elements for that axle? I would say no. If you go to a workshop, you don't know it. There is no guy that asks you, please tell me E, J, eta, zeta, and J, zeta, and then I will start my work and add some masses here and there. So there must be some kind of machine or something that helps you in balancing your rotor or your axle of your car. And basically, there is not only one machine, but what I would like to show to you is that there are two different kinds of balancing machines, and they work with different measurement principles. So what could we measure here? Well, we can measure at the bearings, right? We can try to determine the force that acts on the bearing by measuring the forces, and we can also try to measure the displacements that would be there at the bearing. And this is called the force measuring balancing machine and the displacement measuring balancing machine. For the first principle, measuring the forces, this works well in the low speed regime. So you can do it if you stop, for example, your car or the rotor, and then you do some measurement in hard and rigid bearings for very low speed. And from this you can determine the forces, and from the forces you obtain, of course, the counteraction. That is, you can obtain the centrifugal forces that you have to add here, and everything is nice. On the other hand, if you measure displacement, then this works best in the supercritical range. And this is very interesting if you have a high-speed rotor and you don't want to stop it. That is, you don't want to interrupt your work or the whole process there in, I don't know what you want to do with that rotor, but there could be many things. You would like to, of course, constantly use your rotor, and you won't like to stop it, balance it, and then restart it again, and then have that transfer through the resonance region and so on. So there are good practical reasons to be able to observe, so to monitor displacements at the bearings during operation, and then knowing how to calibrate, how to determine the imbalance and take some countermeasures only if from the monitoring you would say, but no, my imbalance is too large and I have to do some countermeasures. That's the idea of measuring displacements. However, as we will see, it needs, of course, flexibility in the bearings. It is, of course, naturally included in the bearings, some kind of flexibility, and calibration ones are needed. So therefore, I would like to start with the simpler thing, with the force measuring balancing here. So again, the situation is as before. We have our rotor in stationary operation, low speed stationary operation, and we measure the forces. So now we determine the forces at the bearings, and from these forces at the bearings we determine the forces at the plant. So we choose the location of these plants, and we determine the forces F sub 1 and F sub 2 here. So it's kind of inverse of the problem I would say we studied before. Yeah? So now the bearing forces are measured. We know the distance A. We know, of course, also the distance S sub 1 and S sub 2. So all the geometry is known. And then by a simple balance of torque, I would say, here, we obtain the appropriate forces F sub 1 and F sub 2, and they have to be then, so we do not only obtain the magnitude of these forces, but also the direction of these forces, and from this we can determine of course, the angles phi sub 1 and phi sub 2 to get these directions right. And then we can determine the absolute value, so the magnitude of these forces, by adding at a certain distance, at a certain radius r here, the correct masses. So you can see that this is quite easy. You have a linear system here to solve for the centrifugal forces, and then you are done. For measuring displacements, once you have flexibility in the bearings, the equation of motion become more and more complicated. They include another dangerous effect, namely another possibility of resonance. We did not talk here a lot about resonance, just that we are in the subcritical range with respect to the critical speed to be able to have here the force measuring balancing. And this, therefore, the flexibility of the bearings has to be dealt with care. And how this is done, cliffhanger, how this is done and how we balance a rotor in flexible bearings or by measuring the displacements will be explained to you in the next video. Thank you very much for your attention. Stay tuned.